All right. In the previous page of our notes, this should be filled out completely. I guess 2 pages ago. What is a secant line? What is a tangent line? And what do the slopes mean? So if it's not filled out, fill it out. Okay, it's the bottom left. Okay, secant line is a line that connects 2 distinct points of a function. Here's an example of a secant line. A tangent line is a line that just touches your function at one location, created by 2 points that are infinitely close together. The slope of the secant line, talking a lot about slope, okay, is the average rate of change of the function. The slope of the tangent line is the instantaneous rate of change of the function. How quickly something is changing at a moment in time. Take those out. Okay. Well, before we go any further, let's just get this out of the way. What is a derivative? A derivative is a fancy math word for an instantaneous rate of change of a function or a slope of a tangent. I don't know why I just didn't go to the second line. Let's go. Or slope of a tangent. Okay, it's very, very important moving forward in this class that we understand that these 3 things are equivalent. A derivative, instantaneous rate of change, and slope of a tangent. All the same. Okay, they're all the same. Now today what we're going to be doing is we're going to be finding the exact values for these slopes of tangents. We could find these exact values because we'd be able to find these 2 points and we could find the slope. This is easy to find. But this guy, more difficult. Okay? We talked about like approximating it somehow. And we said, take 2 points close together to a single location. Those would be good approximations. Well, the closer and closer and closer you get, the better and better your approximations until you essentially have the exact value. Okay? So question is, what is this value? What is the exact value? Well, this is a problem that actually wasn't solved long ago, like in relative math terms. Long ago was like back in, the Greek days with Archimedes and Euclid and stuff like that. Like the problem of finding the instantaneous rate of change of a function was solved in like the 1600s, okay? Which is not that long ago. All right, now if they had a calculator, they probably wouldn't have had to worry about it at all. Because if you had a calculator, you could find the instantaneous rate of change of this function, the slope of the tangent, right at 2. Now first, start by going ahead and drawing the tangent line to this 3x squared minus 2 at 2. I want us to make sure we can just understand that the tangent line would look something like that, right? Again, instantaneous rate of change, slope of the tangent. Same thing. Okay? Now, what does that equal to? Well, if you had a calculator, you can plug in 2 points into a slope formula. This is the slope of a secant formula. But if you plugged in 2 points really close together, you'd have a good understanding of what is going on right at that location. Talk to your neighbors about the points that you would use to approximate the slope of this line. Go ahead. Talk to your neighbors about it. Yeah, this is the formula for slope, right? Yeah. And it's usually for points that are far away, and we call that a secant slope.
So points that are really, really close.
Yep. So give me an example of 2 points.
We don't have any y value.
Oh, yes, I do. I have this equation. It can give me any y value.
Oh, well then if we're at 2, I would use 3 and 1.
3 and 1 is too far away. It'd be a good understanding. It'd be a good approximation, but it's too far away. I don't feel comfortable using 3 and 1. Give me other values I should use.
1.9999.
There we go. Okay. So a great, if not the exact approximation would be using 2.000001 and 1.99999. And I know I would get some number, right? Because this denominator is not equal to 0. It's just close to it, but it's a decimal. And the numerator I can actually calculate. And if we had time, we would do these calculations. But I'm going to tell you right now that this is just not realistic. It's not really realistic now to do because we're going to be looking at different functions in different locations. It's going to take us time. We're not able to use our calculator also. And let's think back to the 1600s. They didn't have calculators at their disposal. So this is not realistic. I can't do this all the time. I need to think about this and approach this a different way. Okay? I mean, I can do it. It is realistic now. But it's like, let's go back to the 1600s and think about how they approached it. Okay? And this is what they kind of discovered, and this is what we're going to go through. We're going to look at this function. Okay? And what we're going to do is sketch the tangent slope values on this graph. Of f of x if this is f of x. Now, what I'd like us to start by doing is I've designated 5 distinct points. I'd like us to sketch very small, tiny tangent lines to our graph at those 5 locations. So example like this one, I sketched this guy. Why don't you guys sketch the other 4? The small, teeny tiny tangent lines. Now, if I knew this equation, eventually I'd try to find out what this exact value is. But for right now, I'm just going to go ahead and approximate the value of this slope. Okay? Now, discuss with your neighbor, what type of value would you see with this slope? Go. Just the slopes. Yep. Steep negative, right? Very large negative. All right, we would see that this would be like a negative value, a large negative value, right? What I'm going to do is sketch that approximation of my tangent slope value over here. And I'm going to say at -2, I have this larger negative value below my x-axis, right? Negative values for y. All right, well, this value here, this is going to be a negative slope value, but it's a little bit less negative than this. It's not as steep. So this may be like a negative, 8, and this is like a negative 1 or something like that. So I'm going to go ahead and plot a less negative value there. I'd like you guys to plot the remaining tangent slope values here when x is 0, when x is 1, and when x is 2. And then check your plots with your neighbors. It's just a large negative value. Okay? Think of like this, like negative 1, 2, 3, 4, that's a larger negative value.
Yeah, but like, do you mean like since this line is going all the way? So
I'm just saying because the slope is very steep and negative, we're going to be towards the bottom of the negative value.
okay.
We're just kind of estimating here. Just estimating.
So we're not doing like, so this for me, the second one that you just plotted,
Yep.
I would have said that it was positive because
No, this is negative.
negative over negative. Not using.
If a line is going down from left to right, that's a negative slope.
Yeah.
So I'm going down and over. I'm looking at the slope of this line. Not looking at where it's located, I'm just looking at the slope. Does that make sense? So the slope of the line. We know lines have slopes. It's not about where the line is located, it's about the rise over run of this line. I'm going down and over. Down and to the right, that's a negative slope. This line has a 0 slope. When x is 1, this is a little bit positive. When x is 2, this is more positive. Okay, this is very interesting. It looks like our slopes are following a trend. And I could connect them, but I'm not too sure about it. Okay? So let's just double check and let's give us 4 more points in between our values. So I'd like you to plot the tangent slope here, the tangent slope here, the tangent slope here, and the tangent slope here. And see if it does really follow what we are seeing. Okay, so this is a little bit less negative than this and more negative than that. So yeah, this would be negative but less negative than the previous one. This would be positive but less positive than the next one. And this would be between the next two. And all of a sudden I see this. Okay. If we continued to go and looked at different points along this curve and plot the tangent slope values, we would find that, yes, we'd create a line. Now, this is a huge discovery. Why is it a huge discovery? Because this line is, a function. It is something that can be expressed as an equation. I can say the tangent slope values equal whatever this equation's graph gets me. Okay? And when this discovery happened, we said, okay, since this is a function, let's designate this function as something special but related to f. We call it f prime of x. F prime, this prime is just a little tick mark. And what this is showing us that there is an equation that looks like this that will give me the values of the tangent slopes to that. Okay? So there is an equation that will give me or generate the tangent slope values of f. Okay? And we're going to be able to discover what that equation specifically is. Okay? Now, this is a line. So maybe all of these tangent slope equations will look like lines. Well, let's look at some other different types of f of x's like this one. Well, let's go ahead and graph by first starting with 5 distinct points, 1, 2, 3 right here, 4, 5, graphing the tangent slope values. Again, that's what f prime of x is. F prime of x is the tangent slope values of f. Okay, so plot your tangent lines, sketch your teeny tiny tangent lines, and then plot your points. And let's see, does this one create a line? Because man, that'd be sweet if all functions had, tangent slope graphs that are lines. That makes things easy. Check your plots with a neighbor. Now, at 0, this is where people get a little tripped up here. At 0, look at this tangent slope, Miss Lynn. See that little red line right here? What is that value of that slope? It's positive. Good. So at 0, I should have this positive value there. Okay? Now, at -1, this looks like it's a horizontal line. That slope is 0. Okay, so I should have a 0 here. All right, well, let's hope that they go on forever. At the -2, I see a negative slope. Oh, but at 1, I have a 0 slope. And at 2, I have a negative slope. All right, so this one is definitely not forming a line. It looks like we have a parabola. All right, well, we're out of lines, but at least we know this does have the graph of something that we've known and seen before. This has some equation. If we can find that equation, then we can plug in values into this equation, and in plugging values into this equation, giving these points, all of a sudden this point right here, this is telling me that at x equals -0.5, I'm going to have a positive tangent slope, and it'll give me a specific value. At -0.5, positive tangent slope, whatever this y value is, if it's 2, well, that's telling me that that tangent slope's value is 2. That's really powerful, okay? All right, well, just for more practice, let's go ahead and create some more of these f-prime graphs for different situations. We know that they're not all going to be lines, but maybe some of them will be. Try this line out. Check with your neighbor to see what they got. That's right. Yep. Good. Go ahead and sketch your tangent lines if it helps you. Negative, 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 negative. So I see that not only are they negative, but they're negative and consistent, giving me this. Okay? Very interesting. Now this should make sense, and I can actually, you could probably answer me this question. If this was the graph of -2x, what would be the equation for this graph? Why -2, Mr. Dominique? No. Boo. We're not there yet. Anybody else can answer why it's -2? It's the slope of this line, right? A line has a consistent slope. So if I look at the tangents everywhere, all the tangent slopes are going to have the same slope of this line. So this has got to be just the slope of the previous one. That's easy. Okay? Now, let's look at this one. If you already have heard about derivatives and potential rules, keep your mouth shut until we get to next unit, okay? I'm just going to say that right now, okay? All right, I'm going to do this one for you because this one's a little tricky. What I'm going to do is actually pick, 1, 2, but then I'm going to go and pick 2 ones really close to 0. And then I'll pick 2 close to 0 here, and then 2 that are spaced out. So I have 1, 2, and then 2 close to here, and then 2 close to here, 1, 2. All right, I'm going to say this first tangent is a little bit negative, but pretty close to being flat and 0. This next one, still same way. Then if I get here, I see I'm starting to get more negative, and then I get here, I'm talking about very negative. So my graph ends up looking like this for f prime. If I go over here, I'm at super duper negative values to start with, and then less negative, practically 0. Okay, so turns out these equations of these tangent slope values are going to be very different, but we can see they're kind of related to the previous one. All right, now one more practice before we get to finding the actual equations that we can use to find tangent slope values. Go ahead and answer this. If this is f, find the correct f prime, a, b, or c. If you'd like to, you can pick some points. Plot the tangent slopes. Talk about the tangent slopes. You can do it yourself. Okay. I look at the tangent slopes. I see I have a positive, then a 0, then a negative, then a 0, then a positive, more positive. So it's not this one. This is just negatives and positives. Here's got 2 zeros, and this has got 2 zeros in the correct locations. Here and here, you should have a 0. But positive, 0, negative, 0, positive, this guy. Okay? Now, this has some sort of equation in terms of x's. If this had an equation of x's, this is going to have an equation. But we can plug in values, find points on this, and that y value is telling me the exact slope of the tangent here. Okay? This is kind of the other way about getting to these tangent slopes without using 2 points infinitely close together because we don't have access to a calculator all the time. We'll find that this is going to be easier. Okay? Let's go ahead and find this way to find these tangent equations, tangent slope equations, not tangent slopes, for all functions at all points. That's tangent. Okay? How can we find these f prime equations? All right, well, I'm going to take a random equation. This is a random equation. I'm going to focus on this point right here, which I'll call just a random x point. And my goal is to create a tangent line right here at x. Okay, I want to get there. But I'm going to start with 2 points, and I'm going to have a secant line. Now, the second point, I'm going to designate as having a distance from the first point. I'm going to say if we add h, we get to the second point's x-coordinate, which is just x plus h. Now, if this is x here, this y-coordinate would be f of x, and this y-coordinate up here, to that point, would be f of x plus h. Okay, now I'm going to find the slope of this red line to start. Now, let's recall our slope formula. We're just talking about slopes here. So let's use the slope formula. There's nothing new. Nothing fancy. Slope formula. Well, in this situation, the slope of a secant line, this secant line, I'm going to replace, let's just call this A, this B, and then this would be f of A and f of B. Why don't you guys go ahead and substitute this, and this in for the correct spots in your slope formula. And we'll have the slope of the secant for a function at any location here. So you get f of x plus h minus f of x all over x plus h minus x, right? We did that. That is something I can do right off the bat that I see that will help simplify this equation that I have. What can I do? X's go away, right? The x minus the x goes away. So I now have the slope of a secant in this situation is f of x plus h minus f of x all over h. Question? Great. Now, I don't want a secant line. I want a tangent line. I want a tangent line right at x. I need to take this point right here, and I need to move this point to be infinitely close to the other point. Can't be on top of it, because if it was on top of it, my slope would end up being 0 over 0. It's not going to exist. But I need to get it infinitely close. Now, you guys discuss with your neighbors what happens with this thing when we take that point and make it infinitely close to the other point. Go. All right, Mr. Alexander, what happens to H? Infinitely small number. It's going to approach what number? 0. Now, what is the concept we've been using to get values really, really close to something, but not exactly on top of something? Limits. Right, lefts and rights, limits. So all of a sudden, for this now red line, which is a tangent line, I'm going to take the limits as h approaches 0 of this formula. Oh, that is not looking nice. When you're standing next to it, the whole perspective gets changed about what is straight. Now, what is this? This is just a slope formula. This is slope of tangents formula. I'm going to call this a magical slope of tangents formula, because if I plug in any function into that formula, I will be able to find tangent slopes to that function at any location using this formula. We actually call this the definition of a derivative. If you want to find these great tangent slope generating functions, these f prime of x's, we will just use this formula. Now, this is just the slope formula of 2 points infinitely close together, if you want to write that as a little note. Slope formula when 2 points are infinitely close together. Okay? There's an alternate form of this. I could also write this as an a and an x and an f of a and f of x and have x approach a. It's really the same. We'll talk about that at a future date, but we're just going to stick with this, okay, for now. All right. Now, skip this point. Let's go straight to a problem. We're going to change up the problems a little bit. I want you to find f prime of x and then use it to find the slope of the tangent to f at x equals 2. Okay, let's start. Well, f prime of x, I'm told, is equal to this limit. All right, now what function are we talking about? We're talking about this function 3x squared minus 2. Talked about it a little bit earlier. 3x squared minus 2. All right, so let's make sure I know that's the function that I'm talking about. Okay, what does that look like? You know, 3x squared minus 2 looks like this. I want to figure out that when x is 2, I have a tangent slope. What is this slope value? Right? That's what I'm trying to figure out right now. But to find this value, I'm going to find that tangent slope equation that I graphed and then use it to find it. I'm not just going to look at one specific location. I'm going to find the entire equation that can tell me any tangent slope value anywhere and then use it. Okay? All right, so I got f of x, but this equation needs f of x plus h. So I need to find f of x plus h. Well, wherever I have x, replace it with x plus h. Use parentheses. You'll have to use this process for your test, or you're going to get a huge multiple part problem completely wrong. Okay? All right, now that I have that, let's go ahead and substitute it into my magical formula. I will take this and put it here. I will take this and put it there. Go ahead and do that. Now, did you subtract f of x like this and use parentheses? Because we're subtracting this entire f of x, so please subtract the entire f of x or you're going to make a mistake. Now, we are finding the limit as h approaches 0. Don't forget, we are finding a limit. Now, first thing I would check is, can I plug in 0 for h? No, I get 0 over 0. So that's not telling you that this doesn't exist. That tells you that we have like a hole and we can find the location of it by algebraically simplifying. We've done limits like this before. What would I do? Distribute the 3, cancel some stuff, hopefully cancel the h, and then plug in 0 at the end. Let's go ahead and do this. This is not new. 3x squared minus 3x squared. That's gone. Yes. Sorry. Negative 2 plus 2. That's gone. I just have 6xh plus 3h cubed, 3h squared left over right here. That's all that's left. Well, guess what? I can factor out an h from that. I can cancel these h's now that I have multiplication. Never simplify over addition. Multiplication, simplifications, friend. And then, there's one last thing I need to do. What is that? Plug in 0 for h. That gives me 6x plus 3 times 0, which is 6x. What does that mean? This is the exact equation for this graph right here. Keep skipping on me. If this was 3x squared minus 2, which it looks close to being 3x squared minus 2, this is 6x. Now, you'll have points on 6x. If I plugged in 2, I get 12, right? Well, guess what the slope of this at 2 is? 12. The points on this graph tell me the tangent slopes on this graph. This is something that I can use, not only just at one location, but at any location to my original function. This is what these mathematicians discovered. They discovered these like buddy functions, these friendly functions that tell me tangent slope values to original functions. They said, I don't have to do 2.00001 and square it and multiply it by 3. I can just use these f prime functions. So the question really was, use this to find the slope of the tangent of f at 2. We will find f prime of 2. F prime of 2 is 6 times 2, which is 12. This is the slope of the tangent to 3x squared minus 2 at x equals 2. Isn't that cool? I think it is. Here are some key things to remember, okay? If I said f prime of 3 was negative 1, this is saying the slope of the tangent to the function, or if I ask you what is f prime of 3, this is asking you what is the slope of the tangent to f at x equals 3. Remember, f prime values, if you plug in x's, you get slopes of tangents to the original function f. Plug in x's, get tangent slopes. Now, what happens when I plug in x's into a function? I get y's. I get the points on my function. Okay? So what we're going to be doing is, looking at graphs, we're going to be looking at not only the tangent slope, but we're going to look at the equation of this line. And we're going to need two things. We're going to need the slope of the line, but we also need one point. Well, this point comes from f of x, which equals y, and this slope will come from f prime of x. F prime gives me the slopes of tangents. F gives me points on my original function. Okay? Okay. Now keep that in mind. Let's do the next question. What is the derivative? What does that mean? Slope of the tangent. Instantaneous rate of change. All the same. Of this function when x is, I'm going to switch this up to -1. Okay, you guys figure out the answer to that. Discuss it with a neighbor. It's really simple. We've done all of the legwork, all of the tough work. Now we can just use what we've already discovered to our advantage. Go ahead, discuss. Some of you will be good with this. Some of you will be like, what? Because we will next unit. We're not there yet. We got to know where things come from before we just jump to it. We'll get there. You'll be able to check your answers a little quicker than everybody else. You'll know that for now. All right, what do we get, Ms. Sanders? -6 is correct, right? We have this great equation which will tell us the tangent slopes to any point of 3x squared minus 2. If I want to figure out what the tangent slope is at -1, plug in -1 into 6x. I get -6. It's phenomenal. Well, now let's write equations of these tangent lines, and then I'm going to graph them on the calculator, and then it's going to look great, and you guys are going to feel great about yourselves, okay? We're going to focus at -1 and 2, not 1 and 3. Let's focus at -1 and 2, because it's easy to see on the graph, okay? Now, very important, when they ask you for an equation of a line, you should be thinking right away, okay, I need this. Right? I need that. So my final answer needs to be this. Now, what are the two things you need for an equation of a line? Your point and your slope. Now let's think about this. We have this graph, 3x squared minus 2. At -1, we got that, and at 2, we got that. We know the slope of this already. We found the slope of this was 12, right? We found the slope of this was -6. That was using f prime. F prime gives us the slopes. But now I need the point. Okay? Where is this location? Where is this location? Well, you get points from your original function. Okay, this is at -1, 1. Not a good location for my graph, but I'll just move the x-axis down, whatever. And this is at 2, 10. Let's just confirm that the slopes are 12 and 6. Again, f prime of x for this equation is 6x. F prime of 1 is the slope of tangent to f at 1. That's 6. Sorry, -1 would be -6. And then f prime of 2 would be 6 times 2, which is 12. All right, let's go ahead and write down the equations now. At x equals 1, -1, I'd have y minus 1 is equal to -6 times x plus 1. And when x equals 2, I'd have y minus 10 is equal to 12 x minus 2. Okay? Now, to graph these, I don't need to solve for y equals mx plus b. I can solve for y equals m times x minus x1 plus y2. I can just add this 1 to both sides. So if you're ever just like checking your work, I advise you use your calculator to check your work. Don't solve for y equals mx plus b. Don't distribute. It just takes too much time. Instead, just add the 1 and add the 10. Now I'm going to put this in bold just so we can see it. Okay? Here is the graph of 3x squared minus 2. Here's my tangent line at -1. And there's my tangent line at 2. Okay? Beautiful. Isn't that nice? We just created those tangent lines. What did we do? Well, we had to find our helper function, our tangent slope generator function, using the definition of a derivative to find f prime. That gives me slopes of tangents. I use my function to find points. Voila. Okay? Let's do this for a different function. Root x plus 1 at a location 8. Now I'm telling you right now, f prime of x is not 6x, right? We looked at all these different graphs of these different functions, and we can tell that, you know, they're going to create different equations here. So don't just assume that it's going to be something simple. We have to discover its tangent slope generator. Okay? So again, we want to find an equation. My end game is a y minus y1 equals m times x minus x1. Might as well do the easy stuff now and find the point. Okay? Now again, remember, we have a function. We are looking at 8. I'm creating a tangent line right at 8. We are passing through this point on my tangent line. Okay? So, to find the point, we are using our function. And I will find f of 8 and give me that xy coordinate. Is it plus or minus 3? The square root of 9, plus or minus 3? No, just 3. That's why this graph looks like this and not like that. Okay, just 3. So this is positive 3, so I have my point 8, 3. So I have y minus 3 is equal to x minus 8, and I need to fill in m. All right, well, here comes the more, involved part. We need to find first my tangent slope generator, f prime of x for f. Now you might need some space, so write small or use like the margins on your right. We know that this is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Let's make sure we understand what f of x is and what f of x plus h is. F of x is root x plus 1. That means f of x plus h would be root x plus h plus 1. Let's go ahead and substitute that stuff in and see what we have. Question?
How did you get f of x plus h again?
You, instead of having x, you replace what x is with x plus h. So wherever I have x, it becomes x plus h.
Plus 1.
Right? You just replace all of your x's with x plus h's. Okay, again, if I plug in 0, I'd get 0 over 0. Not good. But we know a technique to simplify this algebraically. What is it? Not the reciprocal. What's the right word? Conjugate. Multiply by the conjugate. Let's do it. Yep. We remember this. This isn't new. I end up with x plus h plus 1 minus the quantity of x plus 1 all over h times the conjugate. Distribute the negative. X's cancel. 1's cancel. I'm just left with h over h times the conjugate. These h's will cancel, leaving me with 1 over root x plus h plus 1 plus root x plus 1. That doesn't look. Is that my answer? What's the last step? Plug in 0 for h. And let's see what I get. 1 over root x plus 1 plus root x plus 1. Could I simplify that? What is that? 2 root x plus 1. Okay, now, where we stopped back in the day is we would stop with this. But I'd like you to make sure you wrote f prime of x equals this, so that you know this is an important function. This is the tangent slope generating function for root x plus 1. Is this our m? Exactly, Mr. Strauss. This is not our m. This is an m generator. Okay? This is an m generator. You don't plug that in for m, because then it wouldn't be a line anymore. You would instead plug values in to find an m. I need to find the m at 8. So I'm going to find f prime at 8. That'd be 1 over 2 root 8 plus 1. That would end up being 1/6. Okay? What you get is a slope generator, not the slope. We want the specific slope to this function at 8. Well, this slope is 1/6. Okay? Now, before we leave, we need to talk about, are there situations in which we cannot differentiate? What does it mean to cannot differentiate? That means where we don't have a tangent slope. Don't leave yet. Answer is yes. You must be continuous to have tangent slopes. So you can't have a tangent slope at a hole, an asymptote, or a jump. You must be continuous. If you are told that a function is differentiable, that means you're continuous. Okay? So, no tangent slopes at holes, jumps, or asymptotes. Is there any situations where we don't have a tangent slope and we are continuous? Yes. If we have a sharp point We do not have a tangent slope at the sharp point. We call this sharp point sometimes a cusp. We do not have a tangent slope at a sharp point. Why is that? Because it depends on the direction you're looking at. I would draw a tangent slope this way in one direction. If I went in the other direction, I'd draw the tangent slope that way. Okay? Now, there is one more problem that you will be able to see on your video that will use a common denominator to find the f prime equation. So watch that. Your homework is a lot of finding these f prime values using this f prime magical formula. Okay? Okay, let's get to our last example of finding equations of tangent lines, this time for 2 over x plus 3 when x is 1. So again, I want an equation. Equation means my end game is this. Okay, x1, 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 y1 is my point. My point comes from my function. So let's go ahead and find the point. I get 1/2. Okay, so that gives me y minus 1/2 is equal to, I'll have to find the m, x minus 1. Now, what is m? M is my slope, but I want the slope of the tangent. Slope of the tangent comes from my tangent slope generator. Okay, it is not this. It is what this at 1 is equal to. Okay, so let's find it, and then let's plug in 1, and that will be my slope. So to find f prime, it's just the limit as h approaches 0 of f of x plus h minus f of x all over h. I'm going to talk about f of x, which is 2 over x plus 3, as well as f of x plus h, which is 2 over wherever x is replaced with x plus h plus 3. Okay, let's substitute that into my formula. Limit as h approaches 0 of 2 over x plus h plus 3 minus 2 over x plus 3 over h. All right, now we see we have a fraction minus a fraction. I'm going to give this a common denominator of the other one. To do this, you need to multiply by the denominator of the other fraction. So I'm going to multiply this by x plus h plus 3. I cannot just add a plus h in here. There's no like 2 plus h and x plus h plus 3. That does not work. You're not able to do that. So don't do it. Instead, you have to multiply by the denominator of the other one. Here, multiply by x plus 3. And let's see what I'd get. So I'd have 2 times x plus 3 minus 2 times x plus h plus 3 over the common denominator of x plus 3 times x plus h plus 3. And that's divided by h. Don't let this disappear on you. This is the most important part of this problem, because we're going to have to get rid of this so that I can plug in 0 for h. Okay, so we're here. Let me just take this over to another page. There we go. Okay, and let's see what happens now. Well, I'm going to go ahead and distribute this 2. Now, see this minus. Make sure we understand we're subtracting this entire thing. So I'm going to distribute both 2's and go from there. This is 2x plus 6 minus the quantity 2x plus 2h plus 3 plus 6. Sorry. All over. This big denominator. Notice I'm not going to distribute this. It might just make things more complicated. Just going to leave it like this. And I have this 1 over h here. This 1 over h can go over here, so it's just an h. Now I'm going to distribute this negative and have a negative here, and negative here. And then see that I can cancel positive 2x and negative 2x, positive 6 and negative 6. It leaves me with a negative 2h. Well, now that I have, and this h could be here if I wanted to, so maybe we just put it there. And I have multiplication in my numerator. I can cancel these h's. Okay, I'm not going to cancel this h here. It's in another term with addition. I'm going to cancel this h by itself that's being multiplied. Okay, so that leaves me with just negative 2 over x plus 3 times x plus h plus 3. The last step is to plug in 0 for h. And when I do that, I get negative 2 over x plus 3 times x plus 3, which is the same as negative 2 over x plus 3 squared. Okay? That is f prime. That is my tangent slope generating function for 2 over x plus 3. Okay, so knowing that f prime, let's just say if x is negative 2 over x plus 3 squared, then f prime of 1 is negative 2 over 1 plus 3 squared, which is 4 squared, which is 16. Negative 2 over 16 is the same as negative 1 over 8. So that is my slope of my tangent to this function when x is 1. It's negative 1/8. We can graph this and that and confirm. Let's go ahead and do that as the last thing. Two over x plus 3, and I'll have negative 1/8 x minus 1. Notice that I'm not distributing. I'm just going to add this half at the end. Okay. Here's the graph of 2 over x minus 3 at x equals 1. There is my tangent. Okay. And if I zoomed in right at 1, we'd be able to see that we're just going to be touching our function just at that location. So here it is. Here's 1, and then boom, hit that, and then leave it. Okay? Thank you. Make sure you practice your homework as these problems get tricky and they're pretty involved.